Once we have a crystal structure, we can imagine cleaving it along a bunch of different planes. And so we have to have a way of specifying which face of the crystal, which plane we're talking about. And the way we do this is using something called a Miller index. So let me draw some 2D Miller indices first, and then we'll move on to 3D. So imagine I have the 2D analog of a simple cubic, so a simple square lattice like this. Okay, and imagine that we're interested in planes that look like this. Etc. Okay, so we have a set of planes. If we want to write a Miller index for this, it's very simple. We set up a set of coordinates. So here we have x and y. What we do is we choose a point on one of the planes. We'll choose this point here. And we move out in the x dimension until we run into another plane. And we ask, how many steps did we have to take? Well, we just took one step within our lattice, right? Because we can tell that our lattice repeat unit is a square, and so we went one of those squares to the right before we hit another plane. So we just write down 1. Then we say, okay, in the x dimension, how far did I have to go? Or in the y dimension, I had to go 1 as well. So it's 1, 1. Then take a Miller index. You take the reciprocal of those two numbers and clear any fractions if they are there, and then write them like that between parentheses. So this would be a 1, 1 plane. Let's draw another plane so we can see the difference. Okay, imagine that we have the same simple cubic lattice, but now we're looking at planes that are spread apart like this and that are vertical. So we write how far this, go ahead and choose an origin on this plane. We say, how far do we have to go before we hit the next plane in the x direction? We had to go 2 units. And in the y dimension, how far do we have to go until we hit another plane? Well, we're moving parallel to the plane we're in, so the answer is infinity. So write that down. To find the Miller indices, we just take the reciprocal of these two numbers. So we get 1/2 and 1 over infinity, which would be 0. We clear the fractions, so we have to multiply by 2. And we get 2 and 0. And so there are the Miller indices for those planes. That would be the 2, 0 plane. Okay, so now that we're going into 3 dimensions, I commend to you this website, which is where I got the figures I'm about to show you. So you can go there for more practice. Okay, so you can see that on this cell, the origin was the back corner of the cell, and we went forward in the x dimension 1 unit and hit another plane, y dimension 1 unit, hit another plane, z. So we started off with 1, 1, 1, and the reciprocal of that was just 1, 1, 1. So that's the 1, 1, 1 plane. In this case, we started off at the back corner, and we started moving in the x dimension, and we can see that we're not quite ready to intersect a plane. We're about 2/3 of the way there. So if we go another half a cell, we'll get to the place where this cuts across the x coordinate. So we've got 1.5, and we had to go 1 unit to get to the y to intersect the plane. And the z, we can see, I don't know if you can tell, but this plane is parallel with the z coordinate, so we're never going to hit another plane. So that means this is infinity. So we flip all these over. It's a little easier if we write this as a fraction. So we have 3/2, 1, and infinity. So we take the reciprocal of those, and we get 2/3, 1, and 0, and we clear fractions by multiplying by 3. So we have 2, 3, 0 plane. A set of planes that are particularly important are the ones that are the closest packed planes for any particular crystal structure. So if we were to say what plane could be cut on a simple cubic structure that would get a face where the atoms are closest as possible for that structure, this would be the close packed plane. So for the 0, 1, 0 is the close packed for a simple cubic. And because of symmetry, if we looked at the 1, 0, 0 or the 0, 0, 1, all of those would be close packed planes for the simple cubic. For the body center cubic, this is the close packed plane because it goes through the center where we've got that center atom. And so we've got atoms on the corners, corner, corner, and the center of atoms. So another way to think about this is along a close packed plane, the atoms are all touching. So all the atoms in the close packed plane are touching each other. Okay, so for the face center cubic, we look at this plane, we've got an atom in this face on the left-hand side of the unit cell, this atom in the back face of the unit cell. We have an atom in the bottom of the unit cell in that face. So those three. We also have an atom in this corner, and this corner, and this corner. So there's actually 6 atoms in this triangle, and they're all touching each other. So that's the close packed plane for the FCC.